Okay, so at this point we know how to find the necessary information to find for finding the volume of a solid of revolution around both a horizontal axis and a vertical axis. So now we're going to take that information, set up an integral, and evaluate it to find the volume of our solid. So just to recap, we start with a region. This one we're going to rotate around the x-axis. We take one washer. We can find the outside radius by going the distance from the axis of revolution to the outside of the region. Find the inside radius, little r, which is the distance from the axis of revolution to the inside of the radius. We're going to find the volume of this solid, or this washer. We're going to do that several times over, and if you see this, it kind of builds a shape. And if we keep increasing the number of washers here, this approximation gets better and better to the point where if we take the limit as n approaches infinity, or n being the number of washers, we're going to end up with the exact volume of that shape. So let's look at setting up the integral. So to set up to find the volume of a solid generated by revolving a region around a horizontal axis, we are going to integrate from the lower bound, which is the lowest x value of contained in the region, to the upper bound, which is the greatest x value contained in the region. We're going to integrate the function pi big R squared minus pi little r squared. Pi big R squared is the volume or the area of this big cylinder, or this red region here, or the area of the circle from the outside here to the inside here. We're going to subtract the area of the blue part, because that's going to be the hole for the washer, and that's the part we want to get rid of, and that is the little r is the radius of that region, so that area of that blue part is pi little r squared. If we subtract those, we get the area of this red part, which is the part that we want. And then we're going to multiply by dx, because dx is going to be the width, or the height of the cylinder. And the more washers we use, the closer that distance is going to be to 0. And if we use infinitely many, that dx is going to approach 0. So let's take a look at our example from before. So we found that the lower bound of this region, which we have is enclosed by y equals 4 minus x squared and y equals 0. We found earlier the lower bound was 0. We found that the upper bound was 2. We found that the radius of the outside circle was 4 minus x squared. And we found that the radius of the inside circle was 0 because the axis of revolution was attached to it. So now we're going to take that information and set up our integral. So here's the region again. Here's what the shape looked like in 3D. And here's our initial formula, integral from a to b, pi big R squared minus pi little r squared, and times dx, which is the thickness of our cylinders. So we're going to plug in. The lower bound we said was 0. The upper bound we said was 2. Big R we said was 4 minus x squared, and little r we said was 0, which will lead us to this integral right here. So notice we have 0 plugged in the lower bound, 2 plugged in the upper bound, 4 minus x squared plugged in for big R, 0 plugged in for little r. Now we're going to take this and we're going to evaluate using anti-differentiation. So here's our integral again. We can simplify. I'm going to pull the pi out, so pi comes out to the front, and then I'm going to take this would just be 0, so now that's gone. And if we multiply out 4 minus x squared squared, we get 16 minus 8x squared plus x to the 4th. We're going to integrate that. So we get, going too far here, we get pi times 16x minus 8/3 x cubed plus 1/5 x to the 5th. We're evaluating that from 0 to 2. Plug in 2, we get 32 minus 64 over 3 minus 32 over 5. Plug in 0, you just get 0, so that part's gone. Get common denominators, we have 480 minus 320 minus 96 over 15. Simplify, and we end up with 64 pi over 15. So the volume of our solid is 64 pi over 15. So let's look at our second example. So we had the region enclosed by y equals 1 minus x to the third plus 1, y equals 1, and then the y-axis. And we found earlier that the lower bound was 0, the upper bound was 1, the radius of the outside circle was 1 minus x to the third plus 1, and the radius of the inside circle was little r equals 1. And we're revolving around the axis of revolution y equals 0. So once again, we're going to plug in our known information into our integral. But for this one, we're going to evaluate it using the calculator. So here's our formula. Our lower bound is 0. Our upper bound is 1. Big R, we said was 1 minus x to the third plus 1. Little r, we said was y equals 1. So we substitute, and we end up with this integral here. Now it looks kind of complicated, but since we're using our calculator, it's going to be pretty easy for us to figure out. So we'll go ahead and do that. Rewrite it here again. I'm going to take out my calculator. I'm going to go to y equals, and I'm going to enter my big R function into y1, and I'm going to enter my little r function into y2. And I think that's a good idea because, as you see in this integral, there's a lot of parentheses in there. So, if you try to do this all at one time, you can cause yourself, it's really easy to make a mistake. So if you put your big R in y1, little r in y2, I think it's going to make things a little bit easier for you. So then I'm going to do math 9 to get my integral. Type in 0 for my lower bound, 1 for my upper bound, pi, and instead of putting, instead of typing this whole thing out right here, we can just substitute in y1. And you can get that by going to vars, y-vars, function. And you can get the y1, y2, or whichever. So we go vars, y-vars, function, select y1, that's our big R, minus pi, y2 we said was our little r. We're squaring both of those, so it's just like the formula. We're integrating with respect to x, so we type in x, push enter, and then we get that, we get 2.01959, so we'll round to 3 decimal places, so our volume is approximately 2.020. So there's our 2 examples. You got 3 practice problems, so go ahead and give those a shot, and then we'll come back and look at revolving around the y-axis.